We're going to look at optimization problems. And so this is taking the idea of minima and maxima and kind of applying them to real situations where we're actually taking measurements, developing functions. What would it mean to find the minima or maxima there? So optimization as kind of a math technique is trying to find or trying to maximize or minimize an amount using derivatives. So we're trying to find where something, either the biggest number it can be or the smallest. And the steps to optimization, first we want to introduce any variables that show up in our problem, and if relevant, create a sketch or kind of a way to represent how those variables are related. Then you're going to figure out which of the variables is the one you're trying to optimize. Then you're going to write a formula for that quantity in terms of the other variables. And if you need to, you'll kind of substitute and rearrange and organize so you've got it in terms of one variable. Then you're going to locate the minima or the maxima as relevant, and that's kind of the process. So here's our example. A rectangular garden is to be constructed using rock wall as one side of the garden and wire fencing as the other three sides. Given 100 meters of wire fencing, determine the dimensions that would create a garden of maximum area. What is the maximum area? So in other words, we've got these three sides right here, and then a wall. And as you've got that sketch in your notes, you can see that we've got, we'll just call these X and Y. And so we know the area equals X times Y, but we also know that 100 equals 2x plus y. Or in other words, I think as I've got it in the notes, y equals 100 minus 2x. And we want to make a right here as big as possible. So let's write, so we've identified all our variables here. We've identified some relationships between them. The 100 is 2x plus y because, you can see from here, sketching it out, this length along these three sides has to be equal to the amount of fencing we have, and the area is pretty straightforward. So now let's write our area in terms of the other values that we've, in terms of one variable. So it's going to be x times, but instead of y, I'm going to write 100 minus 2x. So now I've got a function of area just in terms of x. So if I find the minimum or maximum of this x, it will let me know what my maximum area is. So a prime is going to be equal to 100 minus 4x. If you distribute and then take the derivative, you should see that we get this. That means that our x, if you do some algebraic rearrangement, should be equal to 25. So let me not write an arrow. Our x should be equal to 25, because if you move the 4x to the other side, set this equal to 0, solve, you get x equaling to 25. That means our y would have to be 50. Because remember, y is 100 minus 2x, so if 2x is 25, we get that. And so therefore, our area is going to equal 25 times 50, which is 1,250 feet squared. Because our textbook, or the textbook that I pulled this problems from, is based in the US, actually I changed it. It should be 100 meters. I preemptively changed that. The original did have feet, but we'll change that to meters there. Because I've reported it as meters here. So that's the idea here. Let's take a look at another example. An open top box is made from 24 inches by 36-inch piece of cardboard by removing a square from each corner of the box and folding up the flaps on each side. What size square should be cut out of each corner to get a box with the maximum volume? So let's start by writing our volume. we know that the volume should equal 36 minus 2x times 24 minus 2x. Because if you look, you can see in the sketch that was given to you preemptively, but we could also imagine, cutting these corners out, they're x by x, so we lose 2x from each, length or width. So that's our volume. It's already in terms of one variable, x, so we can jump straight into finding the derivative. I've done this before, so I'm just going to write that down to save us some time. Well, I'll expand it out for you, and then you can double check it. We get 4x cubed minus 120x squared plus 864x. So when you take the derivative of that, you should get taking the derivative, we should get 12x squared minus 240x plus 864. You'll need to use the quadratic formula for this to solve it, because we'll set it equal to 0. And again, I did this before, so I'll just give you these responses, but you can easily verify this yourself. You'll get 10 plus or minus 2 square root 7, which if you run those into a calculator, that's approximately 4.71 or 15.29. And so we need to, check which of these would be our answer. So we could look to see which of these is a maximum, which of these gives us a minimum. Or in this case, we actually have the answer kind of baked into us, because if you imagine, if x is 15.29, and we look at our original sketch, which is why it's good to draw it, if I took 15.29 from both sides, this short side would get obliterated, because 15.29 times 2 is going to be 30-something, and that's bigger than my side of 24. So that means this one can't be used. So that means our x is going to be 4.71 inches. So if you want to find the volume then, we can go back to our original equation. Volume is 36 minus 2 times 4.71 times 24 minus 2 times 4.71. And again, I've solved this before, so I'll just give you the answer. You can go back and check it yourself if you want to run that algebra. 1,825 inches cubed oh, sorry, we need to do times x. I was missing that from there. That would explain why this doesn't make sense. If you caught that earlier, great. But yeah, this volume here should have the height times the length times the width. I was just solving the area. That's why we got this here. You probably noticed that mistake. So that's the idea behind this. Again, it's just taking derivatives, finding the minima or maxima, and then solving for that and interpreting the results.